Tonight, the solar system pauses in anticipation. Interstellar Object 3I/Atlas, the third verified guest from beyond our stars, is set to skim within 0.19 astronomical units of Mars, prompting all orbiting spacecraft around the planet to scramble for glimpses of its mysteries. Yet this encounter goes far beyond a routine pass. The visitor's vivid green halo, unpredictable tiny boosts in speed, and chemistry dominated by carbon dioxide have already upended the standard guidelines for comets. Telescopes on Earth are on the verge of losing sight, handing the relay over to just a few Martian satellites to uncover the reality. Could 3I/Atlas turn out to be an oddball comet, or perhaps a constructed entity redefining what we mean by extraterrestrial? With the timer reaching 0, hints of breakup, irregular signals, and bizarre spectral features might transform our understanding of cosmic travelers. Will the coming hours expose something phenomenal, or confirm that conventional science still calls the shots? Only 6 hours remain in the observation slot before Earth's line of sight to 3I/Atlas slips behind the Sun. At a distance of 0.19 astronomical units from Mars, roughly 28 million kilometers, the outsider hurdles by the crimson world right as ground-based gear fades out. This communications blackout stems not from equipment issues or oversight, but from the layout of space itself. For a short while, Mars emerges as the sole observatory in the solar system. Key orbiters like MAVEN, Mars Express, and ExoMars Trace Gas Orbiter pivot to intensive monitoring, their operators executing pre-planned routines while adapting spontaneously. Deep in the MAVEN operations hub, the elite Red Watch team assumes command. These specialists, prepared for emergencies, navigate decision trees for any conceivable irregularity. In the lead-up to the darkness, they practice swift transitions from routine data collection to high-speed spectral analysis, poised to adjust if an unexpected burst or fragment warning appears on monitors. Reserve setups are in place. Verifications sync with colleagues on TGO and Mars Express. All instructions get recorded. Every bit of information receives a duplicate transmission. There's zero tolerance for breakdowns when the wider solar system can't see. The timeline allows no slack. Mars Express captures wide-spectrum photos at short intervals, layering shots to detect the slightest trace of splitting or trajectory shifts. TGO's analyzers scan the halo for unfamiliar light signatures. MAVEN's detectors for particles and magnetic fields track disturbances in the ionosphere, seeking signs of artificial influences. Each probe's energy and data links pushed to their extremes, with viewing times bargained down to seconds. Should a debris shower loom, Mars Express can flip to protective viewing protocols, trading observations for safety. The cutoff for halting stands 30% beyond the previous peak in material density. This Earthside silence represents more than a mere signal lapse. It's a trial for the whole framework of planetary exploration. The Red Watch Coalition serves as the central hub, forwarding directives and findings via tight relay periods, emphasizing device integrity and linking with rovers like Perseverance and Juno. In mission centers, timers tick alongside the object's inbound path. Beyond the facilities, hobbyist networks tune in for initial photometer readings, primed to feed results into the worldwide notification system. During these 6 hours, the outcome of the watch, and the verdict on whether 3I/Atlas marks a stellar curiosity or a fabricated phenomenon, hinges on a small group of satellites and their crews. The pressure mounts genuinely. The leeway for mistakes cuts sharp. As the opportunity tightens, each moment turns into a possible pivot. A series of puzzling transmissions has trailed 3I/Atlas from its initial spotting. The first clues emerged from a home observatory in Pune, India, where citizen scientist Priya Rallo observed a recurring flicker in the brightness pattern, rising and dropping in a cadence that no comet guidebook could justify. Her report sparked interest, but the peculiarities grew as expert facilities tuned in. Photometric logs reveal the entity's luminosity jumping at intervals too consistent for sporadic gas releases. These rhythms, separated by almost even pauses, contradict the irregular, fleeting bursts common in ordinary comets. Every peak hits with a crisp start and a smooth fade, resembling toggles flipped by an invisible force. Even nearing the Sun, The rhythm stayed clear, unaffected by range or sunlight interference. Spectral examination revealed another shock. Rather than the expected water vapor markers, carbon dioxide dominated every reading. The CO2 to water proportion exceeded 8:1, far surpassing the gaseous known comets by a full magnitude. Such a composition proves so uncommon that simulations in labs barely replicate it. Accompanying the CO2, the halo shines in emerald hues, cresting at 516 nanometers. This shade endures across tools, verified by both earthbound and space-based instruments. The typical culprits, C2 swan bands, carbon monoxide, and other emissions, fail to explain the strength or the steadiness of it. The greenish tint of the coma stands out prominently. Emission lines from nickel, particularly those at 337 and 380 nanometers, dominate over iron by factors exceeding 4, flipping the pattern observed in all documented comets from our solar system. Observations through imaging and polarimetry reveal further intrigue. The coma's verdant glow pairs with a pronounced negative polarization feature, a characteristic more typical of select asteroids than frozen cosmic travelers. The dust tail displays particles that are bigger and less swift than typical cometary grains, following paths that defy straightforward simulations. These particles meander in a wide, sluggish curve, as though ejected by a process that dispenses material in controlled spurts rather than erratic streams. Astrometric measurements, on the other hand, detect subtle accelerations, minor adjustments that fail to match any familiar outgassing patterns. Each slight shift aligns with a flare in brightness, implying a connection between luminosity and movement. No isolated oddity exists in vacuum. Collectively, they paint a picture of an entity that defies conventional classifications. Photometry, spectroscopy, and astrometry all contribute to an expanding file of enigmas. The data accumulates, awaiting a unified theory that accounts for every detail. Planetary experts initially relied on fundamental disciplines, physics and chemistry. For primary theories, each rooted in proven frameworks, have been evaluated against the mounting peculiarities of 2I/Atlas. One theory emphasizes chemical formation in extreme frigid conditions. Here, 2I/Atlas originated in regions distant from stars, where water solidifies and rarer ices like carbon dioxide, carbon monoxide prevail. Comets from the Oort cloud suggest such compositions. Yet none exhibit a carbon dioxide to water ratio as skewed as 8:1. Nonetheless, proponents argue that interstellar realms are immense and our sample minuscule. An anomaly might redefine cometary makeup. A second approach focuses on internal architecture. Buried volatile reservoirs, holding captive gases, could burst forth as solar radiation penetrates the surface. If unevenly placed, these could account for the periodic brightness variations. Experiments in labs demonstrate that minor thermal gradients can ignite abrupt ejections, potentially recurring in layered structures. Such periodicity, while uncommon, remains feasible after eons of space erosion. A third idea involves dust behavior. The coma's jade hue and the abundance of hefty, sluggish grains might stem from atypical dust makeup or grain sizes. Interactions with the solar wind and Mars's feeble magnetic field could sculpt the tail, guiding ionized particles into expansive sweeps. Simulations of cometary tails indicate that under specific configurations, denser grains trail slowly, forming gentle bends that resemble the observed releases. The negative polarization signal, akin to that in asteroids, may indicate dense, carbon-laden particles instead of fluffy ice. Lastly, certain experts highlight shortcomings in current simulations. With just 2 prior interstellar objects cataloged, each newcomer challenges our predictive tools. The fine accelerations and aligned pulses might arise from dynamics our codes haven't yet modeled, like nuanced effects from solar heating, gas venting, and rotational dynamics. In this perspective, the quirks signal gaps in knowledge, not deliberate design. For every riddle, researchers insist on exploring all conventional causes before entertaining unconventional ones. Over these 6 hours, Mars serves as the solar system's sole vantage point. 3 spacecraft, MAVEN, Mars Express, and the ExoMars Trace Gas Orbiter, anchor the observational network. Each deploys specialized tools to record unique aspects of 2I/Atlas's flyby. MAVEN's ultraviolet imaging spectrograph, optimized for dim signals, scans for UV signatures in the tail, focusing on breakup indicators or sudden flares. Its detectors for particles and magnetic fields operate at peak speed to spot fluctuations in Mars's ionosphere. A surge in ions or a field distortion might reveal influences beyond routine processes. Should the comet's dust or plasma engage the air, MAVEN's instruments would detect the impact first. Mars Express employs its visible imager and infrared spectrometer for upfront visuals. Series of wideband images monitor the coma for signs of division or morphological shifts. The spectrometer, ranging from UV to IR, hunts anomalous lines, unforeseen emissions, or depleted water signals. Its Aspera 3 package tracks high-energy ions that could expose atypical comet-planet exchanges. The ExoMars TGO's NOMAD and ACS units analyze the coma for minor gases, seeking odd isotopic mixes or molecular markers alien to local norms. Its CASIS camera, with sharp detail, aims to capture split-offs or active dust flows as they happen. Each device instrument data gets recorded with precise timestamps, cross-referenced live across various teams. At ground level, the Perseverance and Zhurong rovers scan for subtle clues, like atypical dust deposits, shifts in the air, or faint auroras along the skyline. Their detectors and imaging gear offer secondary validation, albeit not as finely tuned as the overhead satellites. The protocol leaves nothing to chance. Patterns of breakup, path deviations post-flare, spectral or radiation signatures that defy logic, isotope mixes beyond solar baselines, or hints of deliberate timing in signals or speedups. Any irregularity spotted by one device demands backup from others. Isolated observations won't cut it. Solely when indicators align from diverse tools and viewpoints does the assessment shift from quirky to groundbreaking. All incoming Mars data endures rigorous scrutiny before joining the official logs. Redundancy kicks off the process. Signals from satellites are copied, timestamped, and archived by separate Earth-based receivers spanning the Atlantic. Such measures shield against solar disruptions, signal glitches, and occasional data spoilage amid communication lapses. Delays in telemetry, which can extend to hours via relay orbits and distant antennas, introduce further ambiguity. Crews fast-track suspicious feeds, those highlighting potential breakups, odd spectra, or sudden course alterations, through swift validation checks. No lone detector or group can sign off on a warning. Each potential incident gets vetted by a minimum of 2 devices, with unprocessed files uploaded to public repositories once capacity permits. Tracking procedures go further than mere figures. When an orbiter sampler picks up a dust particle or icy bit, planetary defense experts intervene. These pros apply rigorous containment guidelines. Specimens get secured, labeled with codes, and recorded via cryptographic seals that need approval from NASA and JAXA alike prior to examination. The aim is ironclad traceability. Any biological traces in Martian soil or skies following the close pass must link back clearly. Upcoming searches for life hinge on distinguishing what came from 3I/Atlas versus native Martian elements. Even ancillary details, timestamps, coordinates, device calibrations, reside in unalterable records, allowing audits long into the future. Beyond the mission hubs, a supplementary web activates. From hobbyist setups in Pune to automated scopes in Arizona, volunteers contribute light measurements and position data to communal stores. An initial heads-up on a brightness surge might arise from a non-professional, yet experts now sift these contributions instantly. Agencies release formal notices only post-multi-tool verification, advocating restraint and vigilance. Bold assertions await ironclad proof. Pre-planned communication strategies for all outcomes emphasize openness sans hype. The info channel stays accessible, yet each phase fosters reliability, duplication, authentication, and provenance, all to yield a conclusion the globe can trust. Within the RedWatch Operations Center, the evaluation framework anchors all discussions. 3 categories: cautious, risky, remarkable. Outline outcomes for 3I/Atlas as feeds arrive from Mars. The cautious route applies if all oddities tie to uncommon yet organic comet actions, like sequential gas bursts, chemically unique particles, or minor thrusts at physics fringes. Risky takes over if breakup or fragment swarms exceed danger lines, such as over 10% mass reduction or erratic paths endangering Mars satellites. Then, protective shutdowns and info sorting eclipse research goals. The remarkable option remains distinct. It requires no fewer than two distinct, statistically robust irregularities, like timed bursts aligning with tiny boosts or emission patterns clashing with established chemistry, verified by unrelated groups and gear. One outlier, however bizarre, falls short. The principle is straightforward. Unified proof alone unlocks notions of artificial origins. Staff grasp the gravity. During this period, the framework isn't merely a diagram. It's the guide for planetary research's future steps. Updated guidelines now mandate swift public sharing of interstellar encounter data within hours, not seasons. The era of withheld comet signals has ended. NASA, ESA, and JAXA all back duplicate depositories where unedited and explained files stream to accessible platforms right after Earth sites verify wholeness. Automated systems highlight deviations. Data streams now facilitate rapid evaluations, with calibration details embedded right next to the measurements. For teams operating Mars orbiters, crisis protocols incorporate condensed, rapid-fire transmissions amid any fleeting occurrence, followed by comprehensive releases of detailed spectral data and photographs. Citizen science has evolved beyond a mere afterthought. Amateur observer groups, spanning from Puna to Patagonia, contribute photometric and astrometric observations straight into validated processing systems. AI algorithms filter, verify against existing records, and flag these submissions for expert review, guaranteeing that initial notifications, often originating from home setups, prompt professional examination in mere moments. Regarding planetary safeguards, the Committee on Space Research's recent proposal requires labeling irregularities on all biological indicator detections after close approaches, along with detailed tracking records for any collected particles or organic materials. These updates aim not only at the upcoming 3I/Atlas encounters, but at all subsequent probes from outer space, embedding accountability, reliability, and an international framework for handling the unforeseen. On October 3, 2025, when 3/Alas approached to within 0.19 astronomical units of Mars, all primary Mars spacecraft and surface vehicles directed their instruments skyward. More than 40 hours of intensive monitoring were sent back from MAVEN, Mars Express, and XMR-TGO, documenting the entity's green luminescence, rhythmic intensifications, and atmosphere rich in carbon dioxide, phenomena unprecedented among documented comets. Although conventional theories account for many aspects, the sequence of subtle velocity shifts and aligned bursts defies clear explanation. The unprocessed datasets, made available for communal scrutiny, form a permanent public archive. Yet pivotal inquiries, including the genuine origin of the outflows and potential signs of artificial involvement, linger without answers. One thing is clear: this close pass has spurred fresh guidelines for tracking interstellar arrivals and established benchmarks for openness. Regardless of what 3/Atlas ultimately reveals, its trajectory past Mars has transformed our strategies for anticipating and discussing extraterrestrial intruders in our solar neighborhood.